In this video, we're going to take a look at the first of two important sets that are associated with a linear transformation. As you can tell by the title of the video, this important set is called the kernel of a linear transformation. And it's not the kernel, for instance, if you're familiar with how operating systems work, and every operating system has a kernel. This is not that type of kernel. It's a very different kernel. So let's give it the definition and then take a look at an example and then see what else we can say about this particular thing. So let T that goes from Rn to Rm be a linear transformation, right? And we know what that means. It has a very precise definition. The kernel, Kernel of T, and it's usually denoted simply by abbreviating the word kernel, K-E-R, and then you put the T in parentheses. So is defined as follows. All right, so our kernel, and it's a set, and it is the set of all vectors in the domain, so all the vectors in Rn, such that when I take the image of those vectors, what do I end up with? I end up with the 0 vector, right? And that's the definition. Not overly complicated. So it basically, when you kind of look at this definition, what it is saying all pre-images all pre-images of the 0 vector, right? And we can kind of visualize it, not a very illustrative visualization, but it works. So let's say we have our two spaces here. So we have our Rn and we have our Rm, and T is this transformation, this mapping that takes elements here and converts them to elements here. So what we're now saying is there is a subset of vectors over here where if all of these vectors, in fact, let me make it more clearly indicated here. So let me take this off. So if now all the vectors that when I apply this transformation get those vectors, they get mapped onto the 0 vector, we refer to this set over here as the kernel of the transformation. Now, when you look at it, again, I want you to think back to a lot of the math that you've done. How many times have you had to find some function and then find its zeros, right? Think of how many times you had to do this. And I'm not just saying a function, but think about maybe a derivative and you setting it equal to 0, or a second derivative and you setting it equal to 0. So the idea of finding roots of a function, right, is very important. It's an important skill, and essentially that's what we're finding now. We're finding the roots, but of a linear transformation. So we want to know all the vectors that when I plug it into this linear transformation will produce an output of 0. It's the same thing when you're finding for instance, the roots of a polynomial. You're looking at what numbers, when I plug them into the polynomial, will give me 0, right? So I just wanted you to realize that this process, right, even though it's in a different context, we're giving it a different name, it is analogous to finding the roots of a function, right? All right, so let's take a look at this, let's take a look at an example of finding this kernel, right? So I'm going to define my transformation like this. So T going from Rn to Rm such that T of V is given by, and what I'm going to do with this example is start with that standard matrix of the transformation. So this will be the standard matrix. All right. And then what does it do? It multiplies my vector, right? So based on this little definition, I know that V has to be elements of R4, right? Because in order for this matrix multiplication to work, V, my vector, would have to have 4 rows. So therefore, our code or domain in this case would be R4, right? So I'll just say, so that in this case, so my n is equal to 4, and then my output, right? My output will be a 3 by 1. Because let's again write down what we know about matrix multiplication. Because if this is a 3 by 4 and V is a 4 by 1, then the output would have to be a 3 by 1. So that means the codomain in this case is R3. All right. So let's see if we can find let's answer this question. So what is the kernel of this transformation, right? So what we're asking for now, we're looking for all the vectors in R4 that when I multiply them by this 3 by 4 matrix, I am going to get the 0 vector in R3. All right, so let's do that. So let V be the generic vector in R4, x1, x2, x3, x4, right? So therefore, if V is in the kernel of T, so if V is an element in this special set, which we're calling the kernel, then this must be true. If I take my matrix 1, 0, 2, 2, 2, 1, 3, 4, 1, negative 1, 3, 1, and if I multiply, right, this element in the kernel, then I would have to get the 0 vector like this, right? Right, so this is kind of the matrix form of this, but when we look at it, we realize what we're actually doing in trying to find the kernel. We're actually trying to find the solutions of this homogeneous system, right? This system here is homogeneous, and we're looking for all the solutions for x1, x2, x3. So yet again, another problem worded in a slightly different way, in a slightly different context, leads to a linear system. So let's put this in our augmented form. Still always think the augmented form is the most efficient way of solving these. In particular, notice that since our coefficient matrix is not square, we couldn't think of using like an inverse, because that's only an option when we have a square coefficient matrix. But since we have a 3 by 4, right, we're going to go back to our trusty Gaussian elimination. All right, and let's see what's going to happen. Now, if you think about this, we know for a fact that homogeneous systems are always consistent. In fact, we already know one solution. If I start with the vector 0, 0, 0, 0, so if I start with the 0 vector in R4, then I will have to get the 0 vector in R3 after doing my matrix multiplication. In fact, that was one of the properties that we previously saw about these linear transformations, that the the image of the zero vector is another zero vector, right? So we know there has to be at least one solution. The question is, are there going to be more? Well, we don't know until we reduce this. We have to put this again in our echelon form. That echelon form, it tells us so much information about the matrix, whether it's square or otherwise. All right. So let's try to eliminate some entries here. So I'm starting with the pivot of 1. So I'm going to take negative 2 times row 1 added to row 2, and then negative row 1 added to row 3. That will eliminate the 2 and the 1 in that first column. So my first row remains as it is. Second row, what does that happen? Well, so we're going to have a 0 there, still a 1 there. This becomes negative 4 plus 3, that's negative 1. Negative 4 plus 4, well, that's 0. And then, of course, 0 plus 0 is 0. Now take the negative of the top row, add it to the bottom row, so we'll have 0, negative 1, 1, negative 1, and 0. All right. So there we go. And now let's see if we can eliminate. So there's our pivot. So let's eliminate. Right. So now to eliminate that negative 1, let's go ahead and do this operation. Let's just take R2 and add it to R3. And we'll have 1, 0, 2, 2, 0. Then we'll have 0, 1, negative 1, 0, 0. And then now just adding, so what do we end up with? So 0, 0, 0, negative 1, 0. All right. So it's almost in echelon form. We just need to multiply that by a negative 1. So if we do negative row 3, that produces 1, 0, 2, 2, 0, 0, 1, negative 1, 0, 0, and then 0, 0, 0, 1, 0. So if we look at this, we can see we do have 3 pivots, right? So we do have 3 pivots, but we do have a free variable, right? So there is no pivot in column 3, so therefore x3 is a free variable. All right. In fact, let's kind of almost like we're doing our back substitution. So the third row is telling me that x4 has to be 0, right? There is no clear definition for x3. That's our free variable. So x3 can be any real number. We're going to just call that t. And then x2, that's equal to, so just be so x2 minus t will be equal to 0. So x2 also has to be equal to t. And then let's solve for x1. So from the top equation, we have x1, and then we have plus 2x3, so that's 2t, plus 2x4, but x4 is 0, and then that's equal to 0. So this means that x1 has to be negative 2t. All right. All right, so we have this, and so we realize that it's not just the 0 vector that will work, right? But in fact, we have infinitely many vectors in the kernel of this transformation. So therefore, the kernel of T is this set. And I'll write my kernel, I'll write my vector as a column, so it's every vector of this form, negative 2t, and then t, and then t, and 0, where t is any real number, right? So any vector of this form, when multiplied by our standard matrix that we defined earlier, will produce the 0 vector. But the other thing that's interesting too is that this vector, so if we look more closely at it, right? So if we take this vector, negative 2t, t, t, 0. Notice I can factor out the t, right? And then that leaves the vector -2, 1, 1, 0, right? So what it means is, again, there are lots of ways we can say it. So this implies that every vector that is a scalar multiple of -2, 1, 1, 0 is a vector in the kernel of T. So every scalar multiple of the vector -2, 1, 1, 0 is an element of the kernel, right? But there's another way we can say it. So that means the span of this vector, right? So since there's only one vector and what we are allowed to multiply it by any scalar, so another thing we can say is that the kernel, right, is the span of that vector -2, 1, 1, 0. So it's the span of the vector -2, 1, 1, 0. In fact, what we can say is we can also say that this vector forms a basis for the kernel, right? So let me just say it like this. So all we need is one single vector, and simply by scaling that vector, right? There's no addition here because there's no second or third vector to add it to, but this, right, represents a basis for the kernel of T. And if you notice, so remember how we defined a definition. So I'm sorry, dimension. The way we defined the dimension is the number of elements or vectors that are in a basis. Since there is only one vector in this basis, right? We say that the kernel of T is one-dimensional. So this implies that the kernel of T is one-dimensional. So essentially, if you would somehow think of this as something linear, right? Something that's one-dimensional, you'd think of it as a line, right? In fact, that's what happens if you take a single vector and you look at all the possible scalar multiples of that vector, you generate a line. So in this case, all the vectors that are spanned by this vector, right, they would represent a single line, and all of those vectors are now, we can identify them as elements in the kernel of this transformation. So they all get mapped on. So let me draw another picture here. So let's say this is my R4. In R4, if I look at every scalar multiple of the vector -2, 1, 1, 0, that produces a line. I'm going to let me sketch that in green. So this line here, right, it represents all the scalar multiples of this particular vector, right? So I'll just say that this is spanned by, and let me call this vector v by v, right? Well, what we've shown now is when we map all the vectors on this green line by this transformation, they are going to end up being mapped onto the zero vector, right? So my transformation takes all the vectors on this line and maps it onto a single vector, which is this zero vector, right? And that makes it the kernel, right? And sometimes your kernel could be one-dimensional like this. There are some instances where the kernel is just the zero vector. So that's the only vector that gets mapped on. But other times your kernel could be higher dimensional. Maybe instead of a line, it could be a plane. That entire plane gets mapped onto the zero vector. It all depends on the matrix. It all depends on how many free variables you come down that you end up with once you put it in your echelon form. But the idea is that now we're able to find essentially the zeros of this linear transformation by solving a particular homogeneous system. Let's do one more example, and then maybe let's do something that's not quite as higher dimensional. Let's look at another example. So let t going from R2 to R2 be defined as, and in this case, instead of giving you the matrix form, I'm going to put it like in the, like the vector form. So let's say it's 2x plus y and then x minus 3. All right. So here's our transformation. It takes vectors from R2, produces other vectors in R2, and let's go ahead and find the kernel, and let's again figure out what its dimension is. Right? Now, if we look at this, we can tell what the standard matrix of this transformation is simply by looking at the coefficients. So t can be represented in the following matrix form. All right, so because I can take, if I take the column x, y, and if I ask myself, and it would have to be a 2 by 2 matrix, right, to produce this 2 by 2 output. So what matrix multiplying this column will produce this column of 2x plus y, x minus 3. Oh, sorry, 3y. Yeah, 3y. There we go. So then that matrix is 2, 1, 1, negative 3, right? So the kernel, so to find the kernel of t, we solve the homogeneous system, right? So 2, 1, 1, negative 3. We want to know what are all the vectors that get mapped onto this zero vector, right? The thing about this, though, is, I mean, we could go through the elimination, but if we realize that the coefficient matrix is invertible, then the matrix equation or the augmented system will always have a unique solution. And in this case, because the system is homogeneous, then that unique solution will be the trivial solution, right? So I'm not even going to do my elimination, right? So since this matrix is invertible, how do I know it's invertible? Well, compute the determinant. So here is the reason. The determinant of this matrix is negative 7, because you'll have negative 6 minus 1, that's negative 7, and that's not equal to 0, right? Then, in fact, this is what I could say. Because I know that the matrix is invertible, then I know it can be reduced to the identity. So if I reduce it to the identity, this is what it would look like. Therefore, x would have to be 0, y would have to be 0. So therefore, x is equal to 0, y is equal to 0. What does this mean? Well, it means that there's only one element in the kernel. In this case, only the 0 vector gets mapped onto the 0 vector. So the kernel of t is simply this, right? In other words, this is the only vector that when plugged into this linear transformation would produce 0, right? Well, if you think about this, so if you were to plot this particular vector, what would you end up with? You would end up with just a point, right? So let's say here is R2. Here now that my domain is a small dimension, I can plot this. And then here is the codomain. Here is the vector 0, 0. But my transformation maps this onto this, right? So that's the kernel. So then what would you say about the basis? Well, the basis is just the 0 vector, right? It's the vector 0, 0. What would you say about its dimension? Well, a point has 0 dimension, right? A point, unlike a line or a plane, a point has 0 dimension, right? So the kernel of T is 0 dimensional. It's not a line, it's not a plane, it's a single point, and points have no dimension, right? So, right, you can have kernels that are of any dimension, basically non-negative, 0, 1, 2, etc. It just comes down to the matrix. It comes down to when you put it in that echelon form. Do you have any free variables that would give you infinitely many solutions to this homogeneous system? In this case, we did not have any free variables because our coefficient matrix was invertible, right? Just one more thing that I'm going to say, and this is just a little bit of terminology. The kernel of the transformation is also referred to as the null space. It's like everything that gets nullified. In other words, everything that gets converted into the 0 vector. So the kernel, right, of T is also referred to as the null space of T. And the word null there has to do with the 0 vector, right? As the null space of T, right? So these are synonyms. Many authors will refer to it as the kernel. Others will refer to it as the null space. And now we know how to find it. And now we can talk about its dimension. And we can talk about a basis for this kernel. All right, see you in the next video when we talk about another important set that's associated with these linear transformations. See you then.